Alrighty, so following that same idea, can we do example 2? So number 2 says, the number of cars that enter a parking lot of a grocery store, T hours after it opens, is changing at a rate that's modeled by the function C prime of T, where C prime of T is measured in cars per hour. Use the table above to approximate C double prime of C and include units of measure. Okay, well, this is interesting because we are already given the first derivative, but they're asking about the second derivative. And so we're supposed to approximate the second derivative. Well, if I approximate the second derivative, I'm going to do that by using slope, right? The slope formula. So I'm going to approximate by using a difference quotient, which is a change in the y's or the change in the x's, or in this case, the change in c prime of t over the change in t. But I need to use values that are close to time 6. So probably the values that I should use are these two. They're kind of around time 6. So how do we do that? We take the output, we subtract the outputs. The order that you subtract the outputs doesn't matter as long as you subtract the inputs in the same order. So I'll notice I took the output of 54 minus the output of 92, then I have to subtract the input of 7 minus the input of 5. While we're here, let's also just go ahead and put the units so that we don't forget. So these numbers, we're measuring cars per hour, whereas these numbers, we're measuring hours. So we finished the problem, just subtract that. So I believe that is negative 38, and then divided by 2. And so my answer is going to be negative 19. But my units are going to be cars per hour per hour. So this is a little funky. The units of my output was already a rate, and I'm going to divide by my input, which is hours. Some people will write it as, so I'm going to put or, negative 19 cars per hour squared. Both of these are correct. Both of these are acceptable. But the idea, again, is when we're taking the derivative, we're approximating by doing a difference quotient, by doing a slope formula, right? We found the answer. But now, because we're given a context, because we're given some units, we can use those units to find the units of the derivative. The units of the derivative are always going to be some kind of ratio. It's a rate, right? So it's always has some ratio of something to something, something per something, and that's what we're getting more practice in is setting those up. Okay, but what if we have to interpret the meaning? So we found the answer, right? We found the answer, or at least the approximation of c double prime of 6. And we found the answer, or at least the estimate of h prime of 2. And we even did it with the units. But what does that tell us? And for that, we're going to remember that there's some things here that we need to declare whenever we interpret a derivative. 4 things. What is the quantity measuring, right? What's the context of the function that's given? Not just like r of x or c prime, but what is that measuring? We're going to include the units in both the answer and the x variable, right? We're going to talk about the specific time where this derivative is being taken, since it's an instantaneous rate of change. And we're going to talk about the word rate. We have to include the word rate somewhere in there. So if you go to the next page, it kind of lays out this nice little sentence stem that tells us how to fill it in, right? It says, name the quantity, so the blank, and then tell me how it's changing. Is it increasing or decreasing? Well, it depends. Is it positive or is it negative? And then mention that it's doing so at a rate of whatever the answer is with units at a specific time measurement. So if I go back, it says to interpret the meaning of the answer that we got in example 1. So I go back to example 1. What was the quantity that was being measured? Because that's going to be the key to setting this up. Well, we were measuring the height of the sunflower. So then I'm going to start by saying the height of the sunflower, was it increasing or decreasing? Well, was my derivative positive or negative? Well, it was positive, so then it's increasing. The height of the sunflower is increasing at a rate, please include this part, is increasing at a rate of, what was the rate? What was the derivative value? Well, we estimated to be 9 inches per week. So at a rate of 9 inches per week, when at time, we found it specifically for time 6, at T6 or T6 hours. This is the meaning of what we found in example 1. We found this. What does that mean? It means that the height, and we not only did we find this, but we found the answer, right? But what does that mean? It means that the height of the sunflower is increasing at a rate of 9 inches per week. When? Oh, at time 6. We need to include that time measurement because we're finding the instantaneous rate of change. I need to know what this measurement, when this measurement is being made. Oh, it's being made at time 6 hours. Okay. So let's try that again. Let's approximate C prime of 1. So this is what we were doing before. C prime of 1, well, I'm probably going to use these two columns of points, right? 0, 16, my input 0, my output 16, my input 2, my output 52, and we're going to say C prime of 1 is approximately 52 minus 16 over 2 minus 0. Now, the top is measuring cans. The bottom is measuring seconds. So when we get our answer, it's going to be cans per second. So let's see the top. So I believe that's 36 divided by 2. So that's 18 cans per second. Let me erase that, make it a little bit clearer. Cans per second. Great, I found the answer. And I found my answer with units. Notice the units of the output on top, the units of the input on bottom. 18 cans per second. But now the second part is, what does that mean? Well, what was the original function measuring? What was this all about? Did we even read the problem? It says the factory produces delicious cans of corn for the typical corn enthusiast. One particular machine is notorious for packaging cans of corn at impressive speeds. The amount of cans this machine has packaged after T seconds is modeled by the differentiable function C of T. So C of T is the amount of cans the machine has packaged. So that's how we're going to start. The amount of cans packaged, you can say by this machine, but I'm just going to say the amount of cans packaged is increasing or decreasing. I have a positive answer. Increasing at a rate of 18 cans per second at time 1 second. So 1 second after the machine started, or maybe 1 second I started measuring, 1 second after I started measuring, the machine is going and packaging 18 cans per second at that moment in time. Maybe it goes faster later. Maybe it goes slower later. I don't know. But at that one instant of time, that's how fast that's packaging. And that's what this finds for us. This finds the rate at which it is packaging. And it's increasing. How do I know it's increasing? Because the amount of cans increasing because of the positive nature of the number. Okay, let's try it again. At the end of the football game, fans begin to exit the stadium. 4 times between 0 and 40, including 0 and 40, the number of fans that have exited the stadium after t minutes can be modeled by the function f of t equals 50,000 divided by 1 plus 535 times e to the negative 0.29t. Find f prime of 8 using correct units. Interpret the meaning of this value in context of the problem. So a couple of things here. I have to find the derivative. They don't tell me how, but I have to find the derivative. Well, I could use the quotient rule, correct? I could use the, I guess I could move this up and try to make it into a product rule. But if we have a calculator, that's probably going to be faster. And whenever I have some exponentials, I know that I'm going to get some decimals. So probably the calculator is going to be the faster way to go. So I'm going to turn on my calculator. And remember, you have access to the calculator as well through your free app. As I turn on the calculator, I want to remind you that whenever you're looking for the derivative, you can go to the math menu and it's option number 8. So I'm going to open the calculator. I'm going to go to math. And option number 8 is the numerical derivative. This helps me find the derivative of any function. I can use whatever letter I want. I'm going to use x. And then I'm going to type in the equation that we're looking for. So alpha x is going to build a fraction. What was that equation? 50,000 divided by, I guess I can go back and forth, 50,000 divided by 1 plus 535 e to the negative 0.29t. 535 times e to the negative 0.29t, but I didn't use t, I used x. Negative 0.29. And so I think I have my function typed in. And now we're going to find it at a specific moment in time. We're looking for the derivative at 8. So the derivative at 8. So this is the one of the 4 allowable shortcuts that you can use on the AP exam without showing any work. You can graph in a appropriate window. You can solve. You can take the numerical derivative and not have to show your work, or you can take the integral, the definite integral, and not have to show your work. Those are the only things you can do in your calculator and not show your work. So I'm about to press enter, and it's going to give me this answer. The answer is 265 point, how many decimal places? 3. 265.590. So I come back over here and I say, okay, I think I got it. This is 265.950. What are the units? Well, what are the units of the function? What is this function finding? The number of fans. So this is that many fans per. And then what is the input unit? Well, the input unit's a minutes. So then this is fans per minute. That's how many fans per minute are exiting at that moment in time when t equals 8. So 8 minutes after they started calculating this, or after the end of the game, then that many fans are leaving. That's the rate at which fans are leaving. But let's write the statement. Our function was finding the number of fans that have exited the stadium. So we can say the number of fans exiting the stadium is, is it positive or negative? Looks positive, so we're going to say is increasing at a rate of 265.950 fans per minute. We're going to come back and talk about why we're going to use decimals or not use decimals. We'll come back to that in a little bit. 65 fans per minute at time 8 minutes. So I wanna reiterate the nice thing about this note sheet is that it gives you kind of the answer, the way you should answer the question, right? The function, well, that would be the number of fans exiting the stadium, is increasing or decreasing depending on what the sign of the derivative is. Well, the derivative is positive, so it's increasing at a rate of, what's the actual answer with units, at time, what's the time? Well, at 8 minutes. You have now correctly interpreted that derivative answer that you found. So we've been focusing on finding derivative values, but now in unit 4, we're talking about interpreting, or what does it mean when we find those answers, right? That's kind of the why of what we've been doing here is now going to come to the why part. In terms of fans per minute, could I have 0.95 fans? I really, so I think it's safer to just put the decimal version, right? Even though it does say fans, so maybe I should say it's increasing at a rate of 265 fans per minute, because I can't really have partial people, especially if it's like 0.26. That doesn't make sense. But let's leave it in decimal form for now, and I think we'll be okay. All right, last one. For times between 0 and 10, the rate that people are getting on an escalator in people per second is modeled by the function p, where t is measured in seconds. Use the graph of p to find p prime of 8. Using correct units, interpret the meaning of this value in context of the problem. So this time they don't give me an equation, they don't give me a table, they give me a graph. And I'm supposed to find p prime of 8. So really that's just a derivative at that point. Well, I can figure out that this derivative, p prime of 8, is exactly whatever the slope of this line is. And it looks like the slope, it goes down 1 to the right 2. So down 1 to the right 2. So that's negative 1/2 is the slope. Now, what is that? What are the units for this derivative? Well, this is talking about the rate at which people are saying in people per second. So that's how many people per second. And then time is measured in seconds. So then per second. So what we're actually finding is the rate of change of the rate of change. And so really, this could also be written as negative 1/2 people per second squared. That's another way to write it. But now let's interpret it. What is it that we're finding? Well, this is telling us the rate at which people are getting on escalators. So the rate that people are getting on an escalator. This is what quantity are we talking about? Oh, this is the quantity that we're talking about. Is decreasing. Why is it decreasing? Because my answer is negative. You have to say at a rate, because we just found a derivative of negative 1/2 people per second at time 8 seconds. This is the interpretation of the answer that we just found in orange. The green part is giving us the context based off of the problem that we were given. So if you follow the layout or the sentence stem, if you will, of how to answer questions of interpret, and you will see in free response questions, you will see find the derivative value, interpret what it means in terms of the problem, something like that. Then this is the statement that you would use, how to interpret the derivative given the original function quantity. You can figure it out by just following that sentence stem and filling in whatever you know about that. What should you know? You should know what the function originally measured. You should know whether it's increasing or decreasing based on the sign of the derivative. You should know the actual derivative value with units. And you should know the time with units as well. Actually, let me go back over here. I wanna correct something on the last one. I just realized we said that it was decreasing because of the negative, so I really don't need to put the negative here. So it's decreasing at a rate of half a person per second per second. That should be it. The decreasing already took care of the negative, so I don't need to write the negative. Over here, I didn't have to worry about that because the increasing was based off of the positive, so then I didn't have to worry about the positive, and I just wrote the number, right? But here, I have to be careful with that. Other than that, pretty easy. We're going to come in the next set of videos, and we'll talk about how to find derivatives in other contexts.